Welcome back, everyone. Ready for another deep dive?
Always excited to explore new topics, especially in the world of quantum computing.
Well, today we're going deep into something that's absolutely fundamental to this field: quantum circuits and architecture.
Think of it as understanding the blueprints and the building blocks of these incredible machines.
Exactly. We have a fantastic source for this deep dive.
Mm-hmm.
An essay by Jörg O. Schneppad titled Quantenschaltkreise, Architektur der Quantencomputer.
Which translates to quantum circuits, architecture of quantum computers.
Schneppad does a brilliant job of explaining these complex concepts, and we're going to unpack some of the most mind-blowing parts for you.
I think a good place to start is with the question of why quantum computing is so different and so powerful.
Right. We often hear about its potential, but I think understanding the underlying principles is key.
Absolutely. It all boils down to quantum mechanics, which governs the universe at a completely different level than what we normally experience.
Yeah, so we're not talking about the physics of everyday objects, but the rules that apply to atoms and even smaller particles.
Precisely. And Schneppad highlights three key principles from quantum mechanics that are essential to grasp: superposition, entanglement, and quantum interference.
All right, let's break these down one by one. Starting with superposition, which I've heard described as a qubit being both 0 and 1 at the same time.
Yeah, that's the core idea, but maybe a more tangible analogy is to think of a coin spinning in the air.
Okay, so before it lands, it's not heads or tails, it's both possibilities simultaneously.
Exactly. That's what a qubit can do, exist in this in-between state, holding both possibilities at once.
And that's what gives quantum computers the potential to explore solutions so much faster than classical computers.
It does. This ability to be in multiple states simultaneously unlocks a whole new level of computational power.
Wow. Okay, so then we have entanglement, which always feels a bit mind-boggling to me. It's like two qubits are linked in a way that defies distance, right?
It's definitely one of the stranger aspects of quantum mechanics.
Like if you measure one qubit, the other instantly changes its state, even if they're miles apart.
Precisely. Imagine those two spinning coins, but they're magically connected. If one lands on heads, the other instantly flips to heads as well.
That is so bizarre.
It is, but this interconnectedness, this entanglement, is crucial to how quantum computers can perform such complex computations.
Okay, and lastly, we have quantum interference. I know from physics that waves can interfere with each other, creating patterns of reinforcement and cancellation. How does that apply here?
It's a similar concept. Just like waves, quantum states can interfere with each other.
So they could either amplify each other or cancel each other out, depending on how they interact.
Exactly. And in quantum computing, we can actually manipulate this interference to boost the likelihood of getting the answer we want.
So it's like guiding those quantum waves to steer the computation in the right direction.
That's a good way to think about it. And to really grasp how we control these quantum phenomena, we need to touch on the mathematical representation that Schneppad describes.
Okay, bring on the math.
Well, it's not too heavy, I promise. The key idea is that qubits are represented as vectors, and their state can be visualized on something called the Bloch sphere.
Bloch sphere, I'm not familiar with that.
Think of it as a sphere, like a globe. Each point on the surface represents a possible state of a qubit.
So is it like the North Pole is 0, the South Pole is 1, and every other point is some mix of those states?
Exactly, like our spinning coin, finding its position somewhere on that sphere. And then we have these things called quantum gates, which are the operations that act on the qubits.
Okay, so the gates are what we use to manipulate the qubits, to change their states.
Precisely. And those gates are described mathematically by matrices, which tell us how a qubit's position on the Bloch sphere changes.
Matrices. I vaguely remember those from linear algebra.
It's all coming back to you. And by understanding how these gates and matrices work, we can actually design and control the behavior of qubits within quantum circuits.
So we're starting to see how these abstract concepts of superposition, entanglement, and interference are actually being translated into a framework where we can manipulate quantum information.
Exactly. And it's important to remember that quantum computing isn't about replacing our classical computers. Schneppad makes this clear as well.
Right. It's not about one being better than the other, but about them serving different purposes.
It's more like expanding our toolkit, giving us a new way to tackle problems that are simply too difficult for classical computers.
So while your laptop is great for everyday tasks, a quantum computer is like a specialized tool for solving specific, really complex problems.
Yes, think of areas like cryptography, materials, science, drug discovery. places where the complexity explodes.
And to understand how we actually build and utilize this power, we need to dive into the world of quantum circuits.
Which is precisely where we're heading next. Think of these circuits as the blueprints for quantum computation.
Okay, so if I'm picturing it right, these circuits are made up of those qubits, which we've been discussing, and the quantum gates that act upon them.
You've got it. And Schneppet does a great job of outlining the key components of these circuits.
So if the qubits are like the actors on a stage, the quantum gates are the directors telling them what to do.
That's a great analogy. And just like a director has a variety of cues, these gates can perform operations like flipping a qubit state, putting it into superposition, or even entangling it with another qubit.
And I remember Schneppet specifically talking about the Hadamard gate and the CNOT gate. What makes these two so special?
Well, the Hadamard gate is kind of like the superposition creator. It takes a qubit in a definite state and puts it into that spinning both possibilities at once state.
Ah, so it's like giving the qubit that initial push to access its full quantum potential.
Exactly. And the CNOT gate, which stands for controlled not, is the key to entanglement.
Right, this is the one where the state of one qubit influences the state of another.
Precisely. It has two qubits, a control qubit and a target qubit. If the control qubit is 1, it flips the target qubit. If it's 0, it leaves the target alone.
So it's almost like a switch that only activates if the control qubit is in a specific state.
You got it. And this seemingly simple operation is what creates that spooky connection between qubits, that entanglement.
Wow. It's amazing how these gates can create such intricate interactions between qubits.
It is. And just like in classical computing, where we combine logic gates to build complex circuits, in quantum computing, we combine these quantum gates.
So we're building up complexity, creating more and more sophisticated quantum operations.
Exactly. And Schneppet emphasizes the importance of designing these circuits efficiently. You want to use as few gates as possible to minimize errors.
Because as we discussed earlier, those qubits are sensitive little things. They can easily lose their quantum properties due to noise and interference.
It's a major challenge in the field. Decoherence is what we call it. And this sensitivity of qubits is why error correction techniques are absolutely crucial.
Error correction. So it's like having a system in place to constantly monitor the qubits and fix any errors that pop up.
In a way, yes. Think about it. Even our current computers have error correction mechanisms working behind the scenes.
Right. But in the quantum world, it seems like it must be much more complex.
It is. And building robust error correction techniques is a major focus of research in quantum computing.
Okay, so we've talked about manipulating qubits within a circuit. But what about the bigger picture? How do we actually realize these circuits physically?
That brings us to quantum architecture, which is like moving from the blueprint to the actual construction of the machine.
So it's about how those qubits are physically arranged and interconnected within a quantum computer.
Exactly. And just like the layout of a city affects its efficiency and functionality, the architecture of a quantum computer is crucial for its performance.
It makes sense. You can have the most amazing circuits, but if they're not organized and connected effectively, the whole system won't work well.
Exactly. And Schneppet outlines several different types of quantum architectures, each with its own advantages and limitations.
Okay, let's start with what Schneppet describes as the simplest one, the linear architecture.
Yes. In this architecture, the qubits are arranged in a straight line, with each qubit only interacting with its neighbors.
So it's like having a single-lane road. Easy to build, but not very efficient for complex traffic.
A great analogy. If information needs to travel from one end of the line to the other, it has to pass through every qubit in between.
It sounds like it could get pretty congested in there.
It can. And that's why for more complex computations, we need architectures with better connectivity. Enter the 2D and 3D grid architectures.
Ah, so we're upgrading to a multi-lane highway where qubits can have more direct connections.
Exactly. These grid architectures offer more pathways for information to flow, making the system much more efficient.
That makes sense. But what about building even larger quantum computers, ones with hundreds or thousands of qubits? Do these grid architectures scale well?
That's where things get really interesting. As we scale up, we need designs that are even more flexible and robust. Schneppet introduces the idea of modular and scalable architectures.
Modular architecture. So it's like breaking down a huge problem into smaller, more manageable pieces.
Exactly. Think of a network of interconnected cities, each with its own specialized functions.
So instead of one massive monolithic machine, it's more like a network of interconnected quantum modules.
Precisely. And each module would contain a set of qubits working together to perform specific tasks.
It sounds like that would make the system more manageable, both in terms of building it and troubleshooting it.
It does. Modular designs offer a lot of advantages in terms of scalability and fault tolerance.
Okay, so we've talked about the layout and organization of qubits within a quantum computer. But what about the physical technologies used to realize these architectures?
That's where the real engineering magic comes in. Schneepat dives into some of the leading technologies for building qubits: superconducting qubits, trapped ion qubits, and photonic quantum computers.
All right, let's start with superconducting qubits, which, if I'm not mistaken, are the most popular approach right now.
They are. Companies like IBM and Google are heavily invested in developing superconducting quantum computers.
And it all relies on this fascinating phenomenon called superconductivity, right? Where certain materials can conduct electricity with zero resistance.
Exactly. It's like having a perfect highway for electrons to flow without any loss of energy.
But how do we turn that into a qubit, something that can represent quantum information?
Essentially, they create tiny loops of superconducting material, and the current flowing through those loops can exist in two distinct states, representing 0 and 1.
So it's the direction of the current flow that determines the qubit state. And these superconducting qubits are known for being incredibly fast, right?
That speed is definitely a major advantage. However, they are very sensitive to noise and have relatively short coherence times.
So they're like the Ferraris of the quantum world. Incredibly fast, but delicate.
A good analogy. Now, in contrast to superconducting qubits, we have trapped ion qubits.
Trapped ions. So we're talking about individual atoms held in place by electromagnetic fields.
Precisely. And we use lasers to control and manipulate these trapped ions.
It sounds incredibly precise, almost like having a team of microscopic laser surgeons.
It is, and one of the main advantages of trapped ion qubits is that they have much longer coherence times than superconducting qubits.
So they can hold their quantum state for longer periods, but they might be a bit slower in terms of operation.
Exactly. It's a trade-off between speed and stability.
And then we have the third type, photonic quantum computers. These are the ones that use particles of light, photons, as qubits.
Right. In these systems, the qubits travel through optical circuits, kind of like miniature versions of the fiber optic cables we use for the internet.
So it's like encoding information in pulses of light. It sounds almost futuristic.
It is. And one of the big advantages of using photons is that they are incredibly resistant to decoherence.
So they're less affected by noise from the environment.
Exactly. Which makes them potentially ideal for tasks that involve long-distance communication.
Okay, so we've got these three main technologies for building qubits: superconducting, trapped ion, and photonic, each with its own strengths and weaknesses.
Yes, and there are other technologies being explored as well. But what's clear is that building a reliable and powerful quantum computer is a huge engineering challenge.
Absolutely. And Schneepat highlights some of the key challenges that researchers are tackling: extending coherence times, figuring out how to efficiently entangle qubits, overcoming the limitations of each architecture type. It's a multifaceted problem.
It is. And it requires a lot of ingenuity and collaboration between physicists, engineers, computer scientists. It's a truly interdisciplinary field.
It's mind-blowing to think about the level of expertise and innovation required to build these machines.
It is. And it's all driven by the incredible potential that quantum computing holds for solving some of the world's most challenging problems.
Which is a perfect segue to our next segment. We've laid the groundwork. Now it's time to explore what we can actually do with these powerful machines.
I'm ready when you are. So are you ready to delve into the world of quantum algorithms?
Absolutely. We've spent a good amount of time understanding the hardware side, the qubits, the gates, the architectures. Now it's time to explore the software, the instructions that make these quantum computers tick.
It's a fascinating area and often gets overshadowed by all the hardware advancements. But as Schneepat emphasizes in his essay, the algorithms are really what make quantum computers unique.
It's like having this incredibly powerful engine, but needing the right set of gears to harness that power effectively.
A great analogy. And Schneepat highlights three key algorithms to illustrate the diversity and power of quantum computation: Shor's algorithm, Grover's algorithm, and the variational quantum eigensolver, or VQE.
Okay, let's start with Shor's algorithm. I've heard it mentioned before, often in discussions about cryptography. What makes it so special?
Shor's algorithm is famous because it can efficiently factor large numbers, a task that's incredibly difficult for classical computers.
Now, factoring numbers might not sound that exciting on the surface, but why is it such a big deal for cryptography?
While many of the encryption systems we rely on today, like RSA, are based on the fact that it takes an impractically long time for classical computers to factor large numbers.
Ah, so like the foundation of their security, this assumption that factoring is computationally too expensive.
Precisely. But Shor's algorithm can do it efficiently on a quantum computer, potentially breaking those encryption methods.
So it's a game changer in the world of cybersecurity, highlighting the potential threat that quantum computers pose to current encryption systems.
It is. And thankfully, this realization has also spurred a lot of research into developing quantum-resistant cryptography, algorithms that can withstand attacks from both classical and quantum computers.
Right, so it's like a race between those trying to build quantum computers powerful enough to run Shor's algorithm and those trying to create new encryption methods that can't be broken by it.
Exactly. It's a fascinating dynamic. And while the inner workings of Shor's algorithm are quite complex, Schneepat gives us a glimpse into how it leverages quantum phenomena to achieve this feat.
Okay, break it down for us. What's the secret sauce?
It utilizes something called the quantum Fourier transform, which harnesses the power of superposition and interference to efficiently decompose a number into its prime factors.
So instead of trying every possible combination one by one, which would take forever, it uses quantum principles to find those factors much faster.
Exactly. It highlights how quantum computers are good at different types of problems than classical computers. They excel at certain tasks that would take classical computers an impractical amount of time.
Okay, so Shor's algorithm demonstrates the potential of quantum computing to disrupt cryptography, both in terms of breaking existing systems and driving the development of new, more secure ones. What about Grover's algorithm? What kind of problem does that tackle?
Grover's algorithm, while not as dramatic as Shor's, is still incredibly useful because it addresses a very common task: searching unsorted data.
Searching. That doesn't sound particularly quantum or groundbreaking. We do that all the time on our computers.
We do, but think about how classical algorithms search. They have to check each item in a database one by one until they find what they're looking for.
Okay, so it's like looking for a needle in a haystack. But instead of a haystack, it's a giant database filled with information.
Precisely. And as you can imagine, if that database is massive, it can take a very long time to find what you're looking for.
Especially if it's completely unsorted and you have no idea where to start.
Exactly. But Grover's algorithm leverages quantum superposition and interference to provide what we call a quadratic speedup for this task.
Quadratic speedup, does that mean it's twice as fast?
It's much better than that. It means that if a classical algorithm takes n steps to find something, Grover's algorithm takes roughly the square root of n steps.
So for a database with 1 million entries, Grover's algorithm could find the target in about 1,000 steps, versus 1 million steps for a classical algorithm. That's a huge difference.
It is. And this can have a significant impact on any field that involves searching large data sets, whether it's scientific research, data analysis, or even artificial intelligence.
So while it might not break encryption systems like Shor's algorithm, Grover's algorithm offers a practical speedup for a task that's fundamental to many areas of computing and research.
Exactly. And Schneepat gives a nice explanation of how Grover's algorithm utilizes something called a quantum oracle.
A quantum oracle. That sounds mystical.
It's not magic, but it's a clever concept. Think of it as a black box that can recognize the target item you're searching for.
Okay, so the algorithm doesn't know where the item is, but it has this oracle that can identify it when it stumbles upon it.
Exactly. And then, through a series of quantum operations involving superposition and interference, the algorithm amplifies the probability of finding that item.
So it's like using quantum mechanics to make the haystack smaller, essentially increasing the chances of finding that needle.
A good way to put it. And this illustrates how quantum thinking can lead to solutions that we might not have imagined with classical approaches.
Okay, so we've covered Shor's algorithm for factoring, Grover's algorithm for searching, and now we have the variational quantum eigensolver, or VQE. What sets this one apart?
VQE is interesting because it's not a pure quantum algorithm. It actually combines classical and quantum computation in a hybrid approach.
Ah, so it's not just running on a quantum computer, it's collaborating with a classical computer as well.
Precisely. And this hybrid approach is proving to be particularly valuable in tackling problems in quantum chemistry and materials science.
Okay, those fields sound a bit far removed from cryptography and searching. How does VQE apply there?
Well, imagine trying to simulate the behavior of a complex molecule. It involves understanding how all those electrons interact with each other, which is a computationally intense problem for classical computers.
It's like trying to model the movements of a swarm of bees, but on an atomic scale.
Exactly. And VQE uses a variational approach, meaning it starts with an educated guess for the solution and then iteratively refines it using both classical and quantum computations.
So it's a back-and-forth process, with the classical and quantum computers working together, each playing to their strengths.
Precisely. The quantum part involves preparing and measuring a quantum state that represents the molecule, and the classical part analyzes the results and adjusts the parameters for the next iteration.
So it's like a feedback loop between the classical and quantum worlds, gradually honing in on the optimal solution.
Exactly. And Schneppat points out that VQE is particularly good at finding the ground state energy of a molecule.
Ground state energy. Refresh my memory. What does that refer to?
The ground state energy is the lowest energy state of a molecule. It's crucial for understanding many of its properties and behaviors.
So it's like finding the most stable configuration for all those electrons within the molecule.
Precisely. And this knowledge has enormous implications for fields like drug discovery and materials design. If we can accurately simulate the behavior of molecules, we can potentially design new drugs and materials with specific properties.
It's like having a quantum chemist on our side, accelerating the pace of scientific discovery.
It's an exciting area, and VQE is just one example of how hybrid quantum classical algorithms are being developed to tackle complex problems.
Okay, so we've covered 3 key algorithms: Shor's for factoring, Grover's for searching, and VQE for simulating quantum systems. It's a good case to the diversity and power of quantum algorithms.
And as Schneppat emphasizes, this is just the beginning. As quantum computing continues to evolve, we can expect to see even more innovative algorithms addressing challenges in areas ranging from finance to optimization to artificial intelligence.
It's exciting to think that we're just scratching the surface of what's possible with these quantum algorithms. But before we get carried away dreaming about the future, let's bring it back to the present. What are some of the real-world applications that Schneppat highlights in his essay?
He does touch on some fascinating areas where quantum computing is already making an impact. Shall we explore those?
Absolutely. Let's see how these concepts are actually being applied in the real world. All right, we've explored the hardware, the qubits, the gates, the architectures, and we've even delved into some of the fascinating algorithms that make quantum computing so unique. But now I'm really curious to see how all of this is being applied in the real world. Does Schneppat highlight any specific applications in his essay?
He does, and these early applications give us a glimpse of the transformative potential of quantum computing.
Okay, so where are we already seeing this technology making an impact?
Well, as you might expect, cryptography is one of the areas where quantum computing is making waves.
Right, because we talked earlier about Shor's algorithm and its potential to break many of the encryption systems we use today.
Exactly. That realization has been a wake-up call for the cybersecurity community.
It has, but Schneppat also points to some exciting developments in quantum-resistant cryptography, right? It's not all doom and gloom.
Absolutely. The threat posed by quantum computers has actually spurred a lot of research into creating encryption methods that are resistant to both classical and quantum attacks.
So it's like a cryptographic arms race, driving innovation on both sides. What are some of the approaches being explored to create these quantum-resistant systems?
Researchers are looking into various mathematical concepts that are believed to be hard for even quantum computers to crack.
So things like lattice-based cryptography, code-based cryptography. It's about finding mathematical problems that are inherently difficult, regardless of the computing power you have.
Precisely. It's like building a fortress with walls so thick that no siege engine, classical or quantum, can break through.
I like that analogy. But alongside these new encryption methods, Schneppat also talks about the rise of quantum communication.
He does. And this is where we see the power of quantum mechanics being used not to break security, but to enhance it.
Right. This is where quantum key distribution, or QKD, comes in. It's about using quantum principles to create secure communication channels.
Exactly. QKD leverages the principles of superposition and entanglement to generate and share secret keys between two parties.
And the key point here is that any attempt to eavesdrop on this exchange would inevitably disrupt those delicate quantum states, alerting the parties to the breach.
Exactly. It's like having an alarm system built into the communication channel itself, triggered by any attempt to intercept the message.
It sounds incredibly secure, but I imagine implementing QKD systems must be quite complex.
It does require specialized equipment and infrastructure. Often it relies on those photonic quantum circuits we talked about earlier to transmit qubits of light.
Ah, so those photons, being resistant to decoherence, are well suited for carrying these sensitive quantum keys.
They are. And the potential for truly secure communication, especially in our increasingly interconnected world, is driving a lot of research and development in this area.
It's fascinating to see how quantum technology is not only creating new challenges, but also providing powerful new solutions in the realm of cybersecurity.
It's a constant evolution, pushing the boundaries of what's possible.
Absolutely. So, moving on from cryptography, what other applications does SNEPAT highlight?
Well, another area where quantum computing is showing promise is in tackling optimization problems.
Optimization. Remind me again what that refers to.
It's about finding the best solution among a vast number of possibilities given certain constraints.
Ah, so it's relevant to all sorts of things. Logistics, finance, manufacturing. Anytime you're trying to find the most efficient way to do something.
Precisely. And these optimization problems can quickly become incredibly complex for classical computers to handle, especially as the number of variables grows.
It's like trying to solve a giant Sudoku puzzle, but instead of numbers, you're dealing with real-world factors and constraints.
That's a good way to visualize it. And this is where quantum algorithms can offer a potential advantage. SNEPAT mentions the Quantum Approximate Optimization Algorithm, or QAOA.
Okay, so this is another example of a quantum algorithm being specifically designed to tackle a particular type of problem.
It is. And while it might not always find the absolute best solution, it can explore the space of possibilities much more efficiently than classical algorithms.
So it's like having a quantum assistant that can quickly sift through all those options and point you in the right direction.
Exactly. And this has implications for a wide range of fields, from logistics and transportation to finance and even scientific research.
It sounds incredibly powerful. And then there's the field of machine learning, which is already having a huge impact on our world.
Right. And SNEPAT suggests that quantum computing could also play a significant role in advancing machine learning.
Now, machine learning is already doing incredible things with facial recognition, personalized recommendations, self-driving cars. How could quantum computers improve upon that?
Well, at its core, machine learning is about recognizing patterns, analyzing data, and making predictions.
And those tasks often involve dealing with massive data sets and complex computations, which can take a lot of time, even for powerful classical computers.
Exactly. And quantum algorithms could potentially speed up that process, leading to faster training times for machine learning models, more efficient data analysis, and maybe even entirely new machine learning algorithms.
So it's like giving machine learning a quantum boost, potentially leading to even more powerful and sophisticated AI systems. It's both exciting and a bit unsettling to think about what that could mean for the future.
It is. And as SNEPAT concludes in his essay, we are really just at the beginning of exploring the capabilities of quantum computing. There are still many challenges ahead, both in terms of hardware and software.
Absolutely. But it feels like we're standing on the cusp of a new technological era, and quantum computing is going to be a major driving force.
I agree. It's a field that demands a willingness to embrace new ideas and to think in completely different ways.
And to our listeners, that's our takeaway message today. Stay curious, keep exploring, and never stop asking questions. Maybe one of you will be the next to make a groundbreaking discovery in this fascinating field.
And if you come across any interesting research or developments, we'd love to hear about it. Perhaps we can do another deep dive into this quantum realm sometime soon.
Until then, thanks for joining us on this incredible journey into the world of quantum circuits and architecture.